Today we will discuss about neighborhoods. Generating neighborhoods. First of all, we will see what's the definitions. Neighborhoods. 2.1 definition. Let X2 or XT be a topological space X naught belongs to X and n subset of X. Then our n is said to be a neighborhood I'm writing as NBT, neighborhood of X naught, or we will say that X naught is said to be an interior point of n, or X naught is said to be an interior point of n, of course with respect to the topology T, if there is an open set, if there is an open set V such that X naught belongs to V and V is contained in N. So this is the definition of neighborhood. That means, suppose we are having a topological space. This is our topological space, naming as X. Now I want to have a neighborhood of a point X naught. So there is some point X naught here. Now suppose a set n containing this X naught is given. Suppose this is a set. This is our n. Now this n is said to be a neighborhood of X naught. The condition is that there should exist a V which contain inside your n. Then we will say that this n is a neighborhood. So we will say that this n is a neighborhood of X. There exists an open set V, but this V is open set such that X naught belongs to V and your V is contained in N. Looking back to definition, see, you have got a topological space and a point in X and n subset of X. Then n is said to be a neighborhood of X naught, or X naught is said to be an interior point of n if there exists an open set V such that X naught belongs to V and V is contained in N. For example, we can consider a real line with a usual topology. Real line with usual topology. Now take the point 1 belongs to R. Okay, 1 belongs to R. Now we want to check, consider your n is equal to closed interval minus 2 comma 3. This is your interval minus 2 comma 3. Now we will say that n is a neighborhood of 1. What should be the condition? If I am mentioning in a real line, this is the point 0, this is the point 1. I got minus 2, somewhere 1, minus 1, there is minus 2. So minus 2, here is 2, this is 3. Okay. Now my this is in usual topology, so my open sets are going to be intervals, open intervals. So minus 2 to 3 only I should consider. Evidently it contains 1, right? No problem. It contains in 1. Next, what you want to see? We want to see that whether there exists an open set which completely contain inside your n and which contain the point 1. Suppose I am taking a neighborhood here. Suppose I am taking an open set here. Suppose I am taking the open set 1, 2, right? So it is contained inside your n. Okay, so I can take my V as open interval 0, 2. Similarly, I can take loads of things are there. So I can take either in this version or minus 1, 2, then minus 1, 3 itself I should take. Then I can take minus 2 comma 3. These all are open set which containing 1. So I can find an open set such that this is completely contained inside your n. This was your n. Okay, this is V and this is n. So what's the conclusion? Therefore, there exists V equal to 0, 2 such that our 1 is contained in 0, 2 and your 0, 2 is completely contained inside your minus 2, 3, that's equal to n. So it says that, which implies that this n, that is minus 2, 3 is a neighborhood of 1. Don't get confused, because in real classes you have studied that only open intervals are going to be neighborhood. Here no need of saying that a neighborhood should be open, because we can have this closed set is going to be a neighborhood of 1. So we can note it here. Note here the neighborhood n need not be required to be open. Need not required to be open, because we have studied that a neighborhood is always an open set and all you have studied in your real class. But here the story is somewhat different. That is, we can have closed set also going to be an neighborhoods. See here, I have taken closed interval minus 2, 3. If I am taking open interval minus 2, 3, then again that is going to be a neighborhood by our definition. Now we will see a proposition. 2.2 proposition. 2.2 proposition. A subset of a topological space, a subset of a topological space is open if and only if it is a neighborhood of it is a neighborhood of each of its points. Each of its points. So this is the theorem or proposition we want to prove. That is, a subset of a topological space is open if and only if it is a neighborhood of each of its points. That means what this proposition says is, suppose you have got a topological space and you have got a set here. It is some V. Now V is said to be open. V is open if and only if some point, if I'm taking arbitrarily from this V, for these all points V should be a neighborhood. Okay, if and only if for every x belongs to V, V is a neighborhood of x. This is the meaning of this proposition. So let us see how we can prove it. First we will assume that this set is open. We can consider this as G. So our usual system is to define open set as G. Okay, so G. So let X be a topological space, be a topological space, and G is subset of X. First, suppose G is open. Suppose G is open. Then what we want to prove? G is a neighborhood of each of its points. Then evidently G is a neighborhood of each of its points. Each of its points. What's the reason? Reason is very clear. Given G is open, take some x belongs to G, then G itself is an open set containing x. Am I right? So we can take V equal to G in definition. We want to get an open set, right? That open set itself is G. So it should be always neighborhood of each of its points. And conversely, what we want to assume? Conversely, G is a neighborhood of each of its points. Conversely, assume that G is a neighborhood of each of its points. Each of its points. Then for each x belongs to G, there is an open set. There is an open set. Let me name it as Vx, such that, what should be our condition? Such that this x belongs to Vx and Vx is contained in G. Then only uh, G is a neighborhood, right? Now, suppose I am collecting such Vx, what should happen? That means, suppose I am collecting union Vx such that x belongs to G. So I will get a collection of open sets, right? Now this union is going to be open. Then, now what is this? It should nothing but G, right? Then clearly, G is equal to x belongs to G union of Vx, which implies G is open, right? Because G we have expressed as union of open sets, so it is open. A node, since each Vx is open, union x belongs to G, Vx is also open. So we have proved the proposition. Next we should note some point. Note, see, suppose previously we had taken the example 0, 1, 2, minus 1 plus minus 2, right? Minus 1, minus 2. Suppose I am finding the neighborhood of 0. Okay, so I want to find the neighborhood of 0. So what about the interval minus 1 by 2 comma 1 by 2? Okay, right here, closed interval minus 1 by 2 comma 1 by 2, right? Then definitely 0 belongs to open interval minus 1 by 2 1 by 2, which is open, right? And this is contained in closed interval minus 1 by 2 comma 1 by 2, right? Now suppose I am taking uh, minus 1 comma 1, minus 1 comma 1. I am taking neighborhood of 0. Okay, so minus 1 comma 1, neighborhood of 0 we are considering here. Minus 1 1, will it be a neighborhood of 0? Yes, of course, because this open set, that is minus 1 by 2 1 by 2, right? Minus 1 by 2 1 by 2 is a set which containing 0 and which definitely contain inside minus 1 comma 1. Now if I am taking minus 2 comma 2, again the same set. So what is the specialty? So these all sets are going to be superset of the neighborhood what I considered first, right? So here we can conclude that if you got a neighborhood n, then any superset is going to be a neighborhood. So not one. If n is a neighborhood of a point neighborhood of a point X, then any superset of N is also a neighborhood of X. Any superset is also a neighborhood of X. Next, note 2. With the intersection of any two neighborhood of a point is again a neighborhood of that point. That means suppose you have got two neighborhoods. For example, in real line, you can take in R2 also. Okay, so I'm taking R2 with the usual topology, right? So I have got a point here. Mention this point as 2, 1. Okay, so this 2, 1, we know that this distance is 2, right? This distance is 1. Suppose I'm taking a neighborhood of this as an open disk. Here we can take closed disk also, no problem, because we have defined the neighborhood like that. So suppose I am taking, this is going to be one neighborhood of the point. This is n1. I am mentioning as n1. Now suppose I am taking another neighborhood of this one. Yes. This is another neighborhood. This is n2. Now what about n1 intersection n2? Will it form a neighborhood? Definitely, because what's the reason is, since n1 is a neighborhood, right? Since n1 is a neighborhood means inside your n1 you can find an open set, right? Some v1. So this is my v1. Now it's given that n2 is also a neighborhood. So n2 is also a neighborhood means you can go for an open set inside your n2. So suppose this is my open set. So this open set is v2. I mentioned as v2. Now I have got two open sets such that this v1 is contained in n1 and v2 is contained in n2. Now what about v1 intersection v2? Will it be open? Yes, since v1 is open, v2 is open, v1 intersection v2 is also open, and definitely which will contain inside your n1 intersection n2, right? Now your point, what was your point? 1, 2, which belongs to v1 intersection v2 and which is contained in n1 intersection n2, which implies your n1 intersection n2 is a neighborhood of 2, 1 or x, right? So whenever you are having two neighborhoods, its intersection is also going to be a neighborhood. What about the union? Union definitely result, right? If this is the case means evidently you will have a open set, right? Next one definition. 2.3 definition. Let x comma t be a space and a subset of x. Then the interior or more precisely the T interior of A is defined to be the set of all to be the set of all interior points of A. Interior points of A. So interior of a set. Defining interior of a set. So interior of a set is defined as the set of all interior points. Okay. Now what was interior points? A point is said to be an interior point of a set X if there exists an open set which containing that point and that set completely contained inside your topological space. Then we will say that it's an interior point. That is, we can write this as that is the set of all x belongs to A such that A is a neighborhood of x. So set of all x belongs to A such that A is a neighborhood of x. It is denoted by A naught, that is A interior, or interior of A, or we will write it as int A. Now we can have some example. The interior of a closed disk. The interior of a, first let us see a simple one. Interior of a closed interval. We have studied this, right? Closed interval, when I am taking a closed interval here, because I am taking 0, 1. Now what should be its interior? The interior means whenever I am taking a point here, I want to have a open set completely contained inside here. When I am taking here, I can again for like this. So up to where I can move? From here to here. So it should be open sets. So from 0 to 1 open set. So interior of a closed interval is open interval, right, with the same endpoints. Am I right? Uh, that is interior of closed interval 0 1 is open interval 0 1. So same way in disk also. The interior of a closed disk also the interior of a closed disk in plane in R2. I can write as in R2 is the corresponding open disk. It's the corresponding open disk. Next, the set of rationals has empty interior has empty interior with respect to usual topology on R. Usual topology on R. What's the reason? Reason is very simple. When you are taking your real line, see, when you are taking the real line, we are having set of rationals. Now, set of rationals. Suppose we have got a rational here. I'm taking one here. So here is 0. Sorry, here is 0. This is 2. Should be minus 1. Like that. Okay. So when I'm having a point, I have to get as 1. That's rational. I want to find this interior, right? So I want to take the open sets. When I am taking an open set here, definitely in this neighborhood we will have points from irrationals, right? Irrationals. So we cannot find an open set which completely contain inside your set of rationals. Okay. So the set of rationals have empty interior. Similarly, the set of irrationals also have empty interior. What about Z? Interior of Z means a set of integers. Again, it is having empty interior. The reason is that when you're having in Z 0, 1, 2, minus 1, minus 2. So whenever you are taking any neighborhood of minus 1 or 1 or 2 etc., definitely it will contain points other than integers, right? So we cannot find an open set in this set such that that open set is completely contained inside your set of integers. So it should also have empty interior. And next thing is interior of an empty set. Next thing, interior of an empty set is empty. Interior of an empty set is empty. So today we have discussed about neighborhoods and interiors. Okay, hope you understood this. What was an neighborhood? Then one proposition regarding neighborhood. Then intersection of neighborhood is a neighborhood. Then definition of interior point or interior of a set. Next, we have seen some examples for interiors. Okay, with this, I'm winding up today's session here. Thank you for your patient listening. Thank you.